Hi everyone, welcome to class. So today is our last session, and we're going to start with a quick review of transactions that we covered online last session. Then I try to be quick on this so that we can have more time of practice. So we do a couple of review of all the material that covered before if we have time. We also spend some time on problem solving, Q&A, depending on what we need to work on. We can work on ER, sample ER modeling, star schema, or any other. So, we started the transaction definition. So, what is a transaction?
A sequence of steps that constitutes
I love how you didn't even report what I was here. So, a transaction is a sequence of steps that have a meaningful business action. Like, for example, when you place an order, when you purchase something. So these kind of transactions cannot be partially done, right? So either the transaction is done or it's failed. And this is very important because we don't want to have any like uncommitted updates or any other unsafe actions in between. So we had also a sample of transactions that we, for example, first inserted into the invoice, and the line table is similar to what you had with order line. So this is the same. It's just to specify what was purchased and how much we purchased and at what price. And then updating the product table, the product quantity, because when we purchase something, we reduce the inventory, right? So we have to update that value and then also update customer balance. This is also a small typo here, should be customer. And then at the very end, we just have a commit, right? So that's your database green light for whether this transaction is committed or not. And if it is committed, it means that it was successful, and then we can permanently save these changes. And then we had acid properties. Stand for what? What are acid properties? A for atomicity. Means means the transaction is either succeed or fail, right? So it means all or nothing. So all operations must be completed, if not, it is aborted. And then we have consistency, which means the database should always follow the rules that it has. For example, all the primary keys, foreign keys, all the constraints that they have should hold before and after the transaction. Then we have isolation, meaning transactions should not interfere with one another. It is like as if they are run one by one, even though they are concurrent. And the durability means when a transaction is completed, the database reaches a consistent state which cannot be lost. So it means once a transaction is completed, it's just permanent, right? So even if the system crashes 1 second later, you still have the database remember those changes. And then we had also example of concurrent transactions when both transactions trying to read the balance of customer A, which is 100, and then for some reason this monitor just okay. For example, transaction 1 here, read 100 and then subtract 50, right? Then transaction 2 also read 100, which is the balance here, and add 25. And then the update from transaction 1 is completely lost because this happened first. So as you see, this is number 3 and this is 4. And this order, as I mentioned before, it could be the other way around. So even if transactions are concurrent, like internally in the database, the clock is much more accurate, and it could be even in terms of like nanoseconds. So let's say in that order, this is the order, for example, 1, 2, 3, 4. And the problem here is that when we update, when the table is updated from transaction 1, it caused the balance to be updated to 50, right? And then transaction 4 updated to 125, and we end up with 125, whereas we want it to be 75, right? So it's like this is just it's like the update from transaction 1 is completely lost. And so this was one problem of concurrent transactions. And then we mentioned that in general, there are 3 typical problems with concurrent transactions. One of them is lost update, which was the exact example that you've seen in the previous slide. The other one is uncommitted data, and also inconsistent retrieval. So lost update means just one transaction is overwriting another transaction update. What we've basically seen in the previous slide. So transaction 4 is just overwriting updates from transaction 3, or sorry, transaction 2 overwrite transaction 2. And then we lost the update from transaction 1. Another problem is uncommitted data. And uncommitted data is just happening when one transaction is reading data that another transaction has not committed yet, or T1 is rolled back after T2 access the uncommitted data. So it simply means one transaction use values that later disappears because transaction 1 let's say update something, but has not committed yet, right? So the changes are not permanent yet. And then T2 tried to read the same data, which is updated now. Let's say T1 updates the price of a product from $100 to $200. And then at the same time that this is updated but not committed yet, the other transaction is trying to read it. So what price does it read? 200, right? The updated price. And then T1, before committing, just decide to roll back for whatever reason to the previous price, which was 100. And now T2 is reading the incorrect data, right? So this is uncommitted data problem. And then we have also inconsistent retrieval problem, which is T1 calculating some summary data while T2 was updating the data. So it's just transaction reading data while another transaction is making updates. So it's just mix of old and new values, and then getting some inconsistent read. And then we have we also mentioned how we can address the concurrency control. So you can think of, as I mentioned, you can think of the scheduler. So the scheduler was one solution. You can think of it as traffic controller for transactions, right? So its job is to just decide what is the order that transactions should be run to avoid all those issues that we discussed, like lost updates, inconsistency, and so on. And what tools does it use? So the scheduler typically uses 2 methods, which is the first one is locking, and the second one is timestamp, right? So locking just ensure that only one transaction can update a piece of information at a time, even though the transactions are concurrent, but we don't want to allow them to override each other, right? And then next one is timestamp, which assigns a global unique timestamp to each transaction. So this ensures that transactions follow a specific order to avoid those issues that we discussed. And then we have an example here that transaction 1, for example, wants to update row 5 in the table. This is table A. So it requests a lock on the whole table. And the database grants this lock, and so while T1 is working on this table, nobody else can update or access this data, right? Then transaction 2 comes in and want to update a different row, let's say for example row 30, and but the table is locked, right? So it must wait because the table is locked. And so it has to wait until T1, that is transaction 1, finishes all its update and commit, and release the lock so that T2 can proceed. And even though this may seem slow, but in practice it is not. And so this is just to ensure that we avoid the issues that I mentioned before. And then we had also examples of resource locking, how the database actually physically prevents transactions from interfering with each other. So here we talked about lock granularity, lock types, and two-phase locking. So the lock can be at any level, right? Different levels. It could be at the database level, table level. For example, the example we had in the other slide, the lock was at the table level, right? Or you can just lock a row or a field and so on. And then we have different types of lock, which is binary lock, and which means either locked or unlocked. But most databases use shared and exclusive lock. So shared lock means many users can read the same data, and exclusive lock is just when you want to write and then it blocks others from reading it because you want to update it to avoid, for example, the last update, right? In case, for example, you roll back or you change the data again, you want to make sure that it's committed before another transaction is reading the data. And then two-phase locking. So the database is mainly using a method called two-phase locking, which is a growing phase, where a transaction is just applying the locks, and then a shrinking phase is when you are releasing those locks. And then we talked about deadlock. So these are, I'm just going fast because we already covered this, right? And then we talked about deadlock, which happens when two transactions each holding lock on like the other one actually, what the other one needs. For example, here, transaction A is holding X, right? And wants to access Y. And the transaction B is locking Y, but for some reason later it wants to access, for example, X, which is locked by A. So at the same time, both transactions, A and B, want to access, for example, X and Y, which are locked by the other transactions, right? So we call this a deadlock. And in these cases, neither of these transactions can proceed because both of them want to access something that is locked by the other one. And this can wait forever. So how can we address that? So there are two methods, two approaches to address or to handle such situation. You can have we can say two philosophies, right? There are pessimistic views and optimistic views. So in pessimistic views or pessimistic locking, we just assume the worst. So we say that, okay, conflicts always happen, and so we have to lock early and we have to lock often. And in optimistic locking, we say, okay, most transactions, in most cases, there are no conflicts, and this is especially true about, for example, e-commerce, where we have more reads, right? And compared to the number of writes, and then say, okay, there isn't going to be much deadlock, so let's be optimistic and don't do locking in advance, and so assume the majority of database operations do not conflict. So process each transaction in three phases. So it's first read and then validate and then do the updates. So let's see the example to just, and then we had example of pessimistic locking and optimistic. So as I mentioned, pessimistic locking just assume the worst and assume that conflicts always happen. So it says, okay, let's lock first. And so it just lock even before you read the data, okay? And so after the lock, we can safely read the quantity and also computing the new value, which is reduced by 5. And then because the data is locked, at this time, no one else, no other transaction can access this, which is very restrictive, right? Because you are locking it for the whole time, even before you start reading the data, and at all these times, other transactions cannot access this. And and then when you are done with your update and everything, then you unlock the table product. Now, in optimistic locking, we assume that we are more optimistic and we say, okay, there aren't much conflicts are rare. So we read the data first. As you see, we read the data first without applying any lock yet. We also calculate, for example, do our computations, computing the new values first and so on. And then we only lock right before the actual update, okay? So as you see here, you read the data, do your calculations and everything, and then lock your product table right before the actual update is happening. And so this update check, for example, the product quantity is still what we, for example, originally read. And then once we did the update, we can unlock the product. So in optimistic locking, so we read and compute first, then we apply the lock, and then we do the update, right? In both cases, we have to lock the table and have to update it, right? Not necessarily table always, it could be at any level, as I mentioned before. And so I'm skipping the poll because I think we did the poll on Zoom. So database recovery, and we also discussed database recovery, and we mentioned that even with good hardware, databases can fail. So, for example, your computer may crash, disk can break, and there could be bugs and many types of failure. And when that happens, your database management system or DBMS should be able to bring the database back to where it was, right, or the correct state. And so recovery is one of the most important and core responsibilities of a database administrator, or also DBMS, and it relies heavily on logging and backup, as we see now. So here you see how the DBMS is actually using different components to recover from failure. So the transaction log, as you see here, the transaction log is recording every action that the transaction performed, right? So we have all the transactions here, and the database change log, which is here, is just storing what is before and after, is just recording the before and after images. Why? Because we want to recover the system and bring it back to either of these states, right? Depending on the situation. So your database also maintain a backup, right? So you also have a backup of the full database. So when something goes wrong, when the system crashes and similar things, we can use the transaction log and also the before and after images to roll back the incomplete transactions, or for example, redo the ones that are completed, so that we can restore the database. And so this database change log can sometimes be called in modern databases just as a log file. So this is the same as database change log. So what is an example of this? Here is an example. So for example, this table is showing what the transaction log actually looks like internally. And so each log entry is showing a transaction ID, the time, the operation, start, modify, insert, commit, right? And the object that is being changed. So you can see also the log instance the data item in the log record here. And then these are the log instances for different transactions. And so as I mentioned, you can use the before and after images to bring back the system to a consistent state. So for example, you can use the before images or old values, as you see here, or for example, the after images for the new values. So if the system crashed, then the DBMS can scan this log to decide, for example, which transactions must be undone and which transactions should be read, right, or redone. And so we also talk about basic recovery facilities, summarizing main tools that DBMS can use to recover the failure, like backup facilities, which provide periodic backup copies. We also talked about journalizing facilities, which just create an audit trail of every change. And they are essential for redoing and undoing transactions. We also have checkpoints which periodically suspend all processing or just working as your staging points, right? And so finally, we have recovery manager that coordinating everything and then just restoring the data and restart transactions after a crash. So recovery by restore rerun. So this is the simplest recovery approach, and we restore just the most recent backup, and then we rerun all the day's transaction from the transaction log that we have, right? So this is very simple. So this is a simple procedure, but the problem is that it can be slow, because imagine if you are, for example, having thousands of transactions and you want to reprocess all those thousands of transactions, it will be very slow. So here we saw the two core actions that we can use during recovery, which are roll back and roll forward, right? So roll back is, and this is where those images that I mentioned before images and after images that your DBMS keep is useful, right? So you can use, for example, before images here for roll back, and you can use after images for roll forward. So what does it mean? So in roll back, we use these before images to undo any incomplete transaction or any failed transaction and return the database to the previous state, right? So we want to go to the previous state. Now, in rolling forward, we do similar to what we do with the redo, right? So we just use the after images, right? Again, from the log that we have to redo committed transactions. So what is the difference? This is for uncommitted ones. Uncommitted incomplete transactions, we roll back. But if it was committed, so if it was committed, then we can roll forward, right? Because we have the after images, and then we can use it for committed transactions. So this is, for example, let's say you have one transaction committed at time, I'm mentioning example for rolling forward. Let's say transaction is happening at 11 a.m. sharp, right? And then crash happens a few seconds later or 1 minute later. So some of the transaction updates may still be in the memory, but they are not still stored on the disk. So the DBMS just use these after images to redo them. And then this is just to ensure that if we had a committed transaction, we can preserve it, right? And then these were other examples, and then summarizing different types of failure, and then how the DBMS can respond. For example, aborted transactions, maybe, for example, because of communication interruption or network problems. These are simply undone using backward, right? Or backward recovery. And then we have incorrect. If we have incorrect data, again, we can use backward recovery or add compensation transactions. And so these can be also fixed by rolling back. So backward recovery is the same as rolling back. And system failure, do not damage the database file. We just restore from the last checkpoint and we roll forward, or we call it also forward recovery. So forward recovery is the same as the rolling forward or redoing, which was for committed or uncommitted transactions. When do you do roll forward? Hello. When do we do roll forward? For committed transactions, right? So we use after images to go to a consistent state. And if it is an uncommitted transaction, if the transaction is uncommitted, we can do rolling backward, right? And next, we have security control, which just talk about how we can protect data against unauthorized access, update, and so on. So we have physical security, password security, and authentication schemas. So the first layer is just your physical protection. Like, for example, keeping your servers in just secure rooms with like having cameras and everything. So this is about physical security. And even if you have like the most secure password, if you don't have physical security, then you cannot protect your data, right? So this is the first and an important layer. We have also the password security, which is just the thing that we all know, but still many people just use like 1, 2, 3, 4, 5 as password. And modern systems also use two-factor authentication, like for example, you may notice it on your mobile phones with Google, for example. And finally, we have also biometric devices or biometric security, which are the things that you are, right? For example, your face, using your fingerprint, and things like that. So the last one, I explained the encryption, and then we can start the code. So encryption protects data even after someone get access into it. So for example, let's say you write a letter in English, anything. So you can write any word that you like. So in plain text, right? And then you want to like encrypt it. So encryption turns that letter into a message that can be only unlocked with a key. So if someone else read it, cannot understand what you wrote. So it's just like you are talking secretly, right? So encryption turned that letter into a message that looks like nonsense. It's like it doesn't have any meaning, but it is actually encrypted. And so in cryptography, encryption is the process of transforming information using an algorithm. We call that algorithm cipher, to make it unreadable to anyone except those processing special knowledge, usually referred to as key. So key is your secret piece of information. So key is very important because without the key, you cannot see what was the real data, right? And so what is the key? It's just usually just a long random number. And it is just controlling how your data is encrypted or decrypted. So we can have an example. For example, for the cipher and plain text. So example of plain text is like, for example, anything, any sentence. Like for example, I'll finish class at 5 p.m. Okay. Now, if I want to encrypt it, there are several algorithms or several methods, we call them cipher, that can do this for us. I'll show you one sample, And within that sample, I will also show you what is the key so that you can better understand how this works. So the result of the process is encrypted information as ciphertext. So if you have that plain text and then you have encrypted it with something that looks like nonsense to you, but is actually the result of an algorithm to encrypt the data, then that's an example of encryption. So, and this is actually how your credit card information is protected, right? As I mentioned before, we do not store credit card information, right? Credit card number directly into your tables, right? Into the credit card table. We want to encrypt the data first. So this is the backbone of the modern database systems. And so let's see the role of the key in encryption. So see this example here. So for example, we just see how these key affect the encryption. And the key here is the word specialty marked in red. And then we can use it to create a scrambled alphabet, which is on the top line. So what does it mean? You define a key, let's say a specialty, right? And this is my algorithm. This is very simple. It is not what actually the DBMS is in practice, but this is just for the sake of an example in the class. Now, let's say your key is a specialty, the red one. And then my algorithm works like this. I say, okay, I write all other alphabets after this that are not included in my key. For example, A, should I write A? No, because A already exists in my key, right? B doesn't exist in my key, so I write B. I don't write C because it's already here. I write D, and I continue the same way. And I write every other alphabet until Z. Only the ones that have not appeared in my key. Now, in the next line, I'm just writing all the alphabets in their correct order from A to Z, right? And so how does this work? We can just, for example, if you want to encrypt a word like, for example, consulting, you can use this mapping to do that. For example, C becomes D. Why? Because here you see C and then you map it to D. O, you can see O, it becomes S. And you have, for example, N, which becomes R. So the word consulting is becoming, after encryption, is becoming DSRAVGHERN, which if you see it somewhere, it's just nonsense, right? But it is actually your encrypted version of the same word. And this is a very important concept to keep your data secure, right? Such as, for example, your credit card information. And then these are just different security controls. So, for example, and these are mainly the security that happens inside your database, right? For example, views or sub-schemas. So how views can help us with the security? Can you imagine that? What is a view? It's a virtual table, right? So view is a virtual table, and it is actually a result of a select statement, right? So for example, you select, you do a query on a table. Let's say you have a frequent query on a table and you decide to store it instead of running it every time, which may be complex and takes a lot of time. You decide to just save the result of that query in a new table. We call it a view, right? And then, do we necessarily have all the columns in the original table in the view? No. You can select just specific columns. Now, let's say your, for example, original column is, for example, storing user information, employee information, things like that, with some information that you want to keep secure. Like, for example, SIN number, right? Or any kind of secure information. And so your view may extract all other columns except the ones that we want to keep them secure, like for example, SIN number. And so this is how, for example, views can help with the security. So let you hide those sensitive columns. We can also have user-defined procedures that control what operations are allowed without giving the direct access, for example, to those tables. And what is a stored procedure? They are just saved piece of SQL code inside the database. For example, we can create procedure, let's say give raise, right? And then then anyone that has the permission on that stored procedure can give a raise, for example, to employees, but they cannot access the employee table directly. They have only access to execute that stored procedure, but not access to the actual table. And then we have authorization rules that decide, for example, who can do what, audit trails, reporting actions for example, accountability, and then we have encryption for data storage and transmission, which protect, store, and transmit the data. So these are just all internal wall of defense for security control. And then here we see how this is just a model of DBMS security. We see, for example, user like Richard, James, and so on, or a group, like for example, accounting group, tellers, shop managers, or any other group, right? So these users or groups can get some assigned permissions, right? So they can have some permissions. For example, the accounting group can update customer table, right? Or for example, James can alter all tables. Who can execute, for example, month-end application. So these permissions are saying who can do what, right? And what actions are feasible, what they can access. And so, for example, when we have accounting can update customer table, it means they have only update permission. Or for example, Eleanor will have, for example, execute permission on a stored procedure. James has, for example, a very powerful permission of altering all the tables, right? Now, this is just how those permissions become rules. So, for example, we can grant and revoke or canceling the operations. For example, we can for example, as you see here, these two actions, insert and read, for different subjects and different objects. So what this table actually shows is just more detailed more detailed authorization logic, right? For example, let's say a sales department here. What type of action sales department can do? It can only do the insert, right? On the customer records, right? So it can insert customer records, but with a constraint, only if the credit limit is, for example, less than or equal to 5,000. And for example, order transaction staff, so the staff in order transactions, they can, for example, read the behavior that they can do, or the action is read. They can read customer records, but they cannot edit it, right? There's no also constraint here. Here's another example, and then we had all questions that we did last session. And finally, we have the sys tables. You can get, for example, sys star to just get all the metadata, which are information about your database, not the actual data. So, for example, when we select star from sys, then the autocomplete is showing all the system views, right? For example, on columns, objects, and so on. And so, for example, you can have select star from sys tables or select star from sys columns and see what it shows. So if you have, for example, sys tables, as you see here, it's showing every table in your database. So this is all tables in your database and some information about them. So as you see, this is not the actual data. This is a metadata, right? These are information about your database. And then syscolumns, this is the table below on the bottom, is just showing every column of every table in your database, right? And this is, you can think of it as your database dictionary, right? So you can access everything here. And when can it be useful? When you are starting, for example, working on a database and you have no idea what it contains, maybe it's a large database and you just want to get some information about it. And that's it.